In this video, I'm going to go through the implications of different conditions in the OLS regression and what we can do once we have got our estimators when we are in different situations. So let's say we want to do some inference. Some examples would be answering questions about estimating the slope. So it could be that we are interested in the effect of a single covariate. It could be that we are looking at an interaction. Lots of situations. We might want to make a confidence interval or do a hypothesis test. We might also just be trying to describe the relationship between two variables. We're in this situation where we've already fit our regression, and you can go look at the mind map or the previous lectures talking about all these conditions and what we care about. And we have fit it, and we've got the correct mean model, and we've got the correct functional form, and our observations are uncorrelated, and they're already fit. Before we keep going, we need to know whether our residuals have non-constant variance. We need to know if they're approximately normally distributed, and we want to know if our sample size is large. When I say large can be pretty small if it's just a departure from normality. However, for big departures from normality with like extreme outliers or really skewed distribution, or if we have a bad non-constant variance or something like that, we are going to need bigger sample sizes. Definitely more than 50. For minor departures from normality, we might only need 10 or 20. If we're in the situation where we have constant variance and normally distributed errors, our estimators are the best, all right? So they're asymptotically efficient. They are the best linear unbiased estimators. They're consistent. They have great properties. For super small sample sizes, they are not efficient, right? Which means they don't have the smallest MSE for like very small sample sizes, but most of the time you're not going to be in that situation. So they're great. They have a known distribution. It is this normal distribution. We can look and we can do inference about our betas. We can do inference about our estimated outcome, lots of things. So the way I've written this might seem a little confusing, but basically it's saying that they're normal with a known variance. And if we want to calculate for an observation, right, like a y, right, or an outcome, we can do it using a vector of covariate values. And that's a little formula there. Now, the one thing about this is that we don't know beta and we don't know sigma squared. So we don't know the true error and we don't know the true beta. But that's why we do the testing, right? We do have to estimate that variance. So we estimate the variance using the MSE. So R is going to calculate it by using the MSE to estimate it, and that's fine. MSE is going to be a consistent estimator of the error, so we're okay there. So what all of this means is that since R is going to output this standard error for our betas and use that when we're calculating, predictive, like confidence intervals or whatever, or predictive intervals even, we can use the output from R and its standard errors to do our tests. Recall that the case when we use the t-distribution is when we have a normally distributed thing and we're estimating the variance. Well, that's exactly the situation we're in right now. So this is a t-distribution that we can use. And we can use it for small n or large n. It's all fine. Everything's cool. So In this case, we use the stuff exactly as is output in R, and everything works out. Let's say instead of having normal errors or approximately normal looking residuals, our residuals don't look so hot. If we're in this case where we still have a large enough sample size, and like I said before, for small departures from normality, it can be pretty small, but for big departures from normality, you want a lot of samples, like over 50, or maybe even over 200 if it's really crazy. We still have pretty good properties here for our estimators. They're still blue. They're still consistent. It's all good. They're just not asymptotically efficient. So they're not the very best, right? They are still asymptotically normal, which is nice. So we can still get those tests and confidence intervals using this asymptotic normality property. Now, the way I wrote this is a little weird again. So the little dot there is like signifying that it is asymptotically normal. And then on this side, I wrote the MSC in there, which isn't technically correct. I really shouldn't have the estimator on that side, but because of the dot, I feel okay about saying that we're talking about an asymptotic thing, and that's consistent, and so I feel like it's all right. But it's not totally correct. So if you're like a math person and you're like, why is that MSE over there? Well, that's why. With the dot, I feel okay about it. So, but you can see that the formulas are still the same. They're still the ones that R is calculating. Everything is cool. We're going to use the Z distribution for our tests and our confidence intervals because, again, asymptotically normal. We're not in the t-test situation, right? However, when n is large, the Z quantiles are really close to the t quantiles. They're not that much different. If you look at any table, right, as it gets bigger and bigger in the degrees of freedom, so as the sample size gets larger and larger, and remember, we're in a large n situation, our t gets very close to our z. So it's okay if we use the t here. When R outputs stuff, it outputs it with the t distribution. We're not going to freak out about that. They're very, very close at this point. So we're just going to use the standard errors and tests as calculated in R. What happens if our variance is non-constant and our n is large? So when our variance is non-constant, we still have consistent and unbiased estimators. That part's still okay. But they're no longer the best estimators. They're no longer blue. There's probably other estimators that are better using different methods like GLM methods, weighted least squares, all these other things. So you can go learn about those things later. The estimators are still asymptotically normal, or if the errors are normally distributed, then they're normal, like they're actually normal and not asymptotically normal. The problem now is that our standard deviation or our standard errors are no longer so simple. There's that like weird sigma in the middle of them. So that's really troubling. That means the stuff that R puts out isn't going to give you the right standard error. And it's not going to use the right standard error to calculate those t tests and yeah. However, the good news is we can estimate this if we have a large enough sample size. We can use the robust variance estimator, calculate this thing, but it's not going to match the standard R output. So you still have to use another function. You can't just write summary and get this. The other thing is you have to have a large sample size. I would say minimum, like, your sample size better be bigger than 50. So once we have that, we can use the robust variance estimator and do our z tests and confidence intervals. Again, for a large sample, z is really close to t, so if you use the t, no big deal. Again, other estimators are likely better than these estimators, but we can still do valid inference with these ones. We just might be able to do a little bit better in terms of our data use. Finally, if we're in the situation where we have non-constant variance in a small sample size, we're in kind of big trouble, right? All we can really say is that these guys are unbiased. We don't really know much more. That means that they are unbiased estimators, so we could talk about like point estimates. That's fine. But you can't really do valid inference on this. So, no test or intervals for us. Anyways, those are your cases, and hopefully this wraps up this section and we can move on to prediction.